Welcome to Hands-On with ROS2. I will give a very brief introduction, not so much about ROS2, but about the structure of the workshop and actually a tiny bit of ROS2 also. So stay tuned here and then we will dive into the hands-on part. So before we start, you can use the time while I am talking to update whatever you have set up already. So you can find all the parts of the workshop here at Bold Hearts. ROS2_workshop. So there's an initial setup you obviously all done already. And for some reasons, because to make it very RoboCup-likey, we have done some last-minute changes. So it's also very helpful if you just go to your home, where you set up, where you cloned this repository, ROS2workshop. And when you are in this folder, just do a git pull to get the latest cool exercises and new developments. And then just do an ADE start. So that probably becomes familiar, appears familiar to you, which is just updating again your ADE. If you have questions in the meanwhile, you can raise your hand or use the chat function. I think Sander is on it in case something is happening. And I will continue from here. So quick overview who we are. So that's from last year, our team photo with a lot of other robots and our robots on shoulders and hands. We are the team Bold Hearts from the University of Hertfordshire. And that's actually a typo. It used to be 2002, but Google Docs changed it to 2020. So actually we are in RoboCup since 2002 and 3D simulation and humanoidly kid-sized. And we found ourselves 2 years ago, again, questioning the perfect framework. And I think many teams went through this already. And then there's a question of efficiency and how can we onboard people and how do we make it nice, easy to manage, but also working on an embedded robot system, which then changed to the idea to use ROS2. Structure of this hands-on. So we are in the middle of this very short intro to ROS2, which takes 10 minutes. And then we dive into the hands-on part, which is showing the setup and an overview. And then we have 3 exercises. Each exercise has a subfolder in the repository. The first exercise it does not involve any coding. It will just give an overview about the ROS2 ecosystem, how to use tools, and familiarize you with some of the vocabulary needed. Exercise 1 is then, there's another type of, you create your own first node, in the language Python, and which is sensing and acting. So yes, and exercise 2 is the advanced features of ROS2, which is essentially the reason, which will show you the reasons why we actually switched to ROS2. So if you have time, it's very, very a good idea to familiarize yourself with that in any case. We will present the setup and the exercise 0 in full. So going through the steps. And this will be done by Sander. I will be on the chat, but I come to that later. And then we introduce exercise 1 and 2. And everybody is going in this hands-on mode. So you are going through this exercise yourself, which I just wrote in the next item. So you can go through the exercise in your own pace. The guides are in the repository, and you can ask questions. So questions, you best use the Zoom chat, but we will be also on Discord if needed. Yes. I thought Discord, we can, for example, use VLC, or you ask us directly. I wonder if someone sees these pop-ups here. Bloody hell. Okay. I cannot see my own slide here. What is this? So yeah, questions. So after the workshop, you can still use the GitLab tracker and ask further questions. We are more than happy to help you with that. So asking questions now. So that's the part. You can raise your hand, yeah, and I can then chat with you. We can find out if we can fix this somehow with using a chat. If it's for some reason a mistake, yeah, with some of the wording, or if it might be interesting for everyone, I will ask you if you want to share your screen and bring this to the whole audience. So that's kind of like in a real workshop, everybody would sit at their chair and do cool stuff, and we would walk around and see if you're all happy and comfortable with the code, and then we have a little chat. So in this time, so I think, I'm not sure if Sander has done it very often. I haven't, not in a virtual environment way. So I think I also have to familiarize myself with it. So bear with us, but I think we will manage this easily. Yes, that's it. So why ROS2? Yeah. So there's a lot to it, and the core idea here is that ROS2 builds on the data distribution service, which is a standard for real-time systems to communicate, which is also used by many larger companies for embedded systems. Yes, we could just use this DDS ourselves, actually. Could, for some reason, just deal with it, but actually it's quite massive. There's a lot of settings, a lot of fine-grained fine-tuning is needed. So the ROS people decided to use it and build so ROS2 around it. So with a set of tools, the capabilities of the robots, packages of the user space, the whole ecosystem is ROS2, which is then sits on top of the on the DDS. So DDS is a system which has modules which are subscribing and publishing and communicate with each other. So this modularization will be part of all the exercises, and we will guide through that step by step. If you want, there's this paper from last year where we talk about ROS2 and the decision-making process behind it, and some cool parts already, like, for example, why it's more efficient, and we do some tiny benchmarks there. So you can just go back to that in case you like that. And just here, a quick idea, so that you familiarize yourself with some of the words. So that's a DDS layer. There are a lot of implementations for this standard. So the fast RTPS, Open Splice, or whoever is willing to implement the full standard. So there are not many who actually implemented the full thing. That's why, from what I know, only these vendors are actually providing everything what ROS2 needs. Then there's the middleware, so ROS2's communication layer with the DDS, and the wrapper using this middleware. So you will find RCL Pi and RCL CPP in this workshop. Both of this will be part of exercise 1 and 2. And also the ROS client is part of the exercise 0. Yeah, where we don't code, but we use just the ROS tool. And we will create the user code using all these parts. And just a spoiler alert here, it's quite cool. So to construct these nodes and to use this architecture, at the end of the day, it can be all squashed into one efficient intra-process communicating binary. But that's just a spoiler for exercise 2. So we wait till then. Okay. Bam. That's it from my side. So Sander, can you stop sharing? Can you help me with stop sharing the screen?
Let me see. There you go.
Okay. Is there? Yeah, I think that's for the overview. I would then now pass on to you, Sander.
Thank you, Marcus. Well, I got the right page in front of me. Anybody have any questions about what we heard so far? If not, then let me share my screen. So you should be able to see the repository that I have in front of me now. Is that correct?
Can I just ask a quick question?
Of course.
Yeah. So this DDS is the main difference between ROS1 and ROS2?
It is one of it, yeah. I mean, it is definitely the biggest change, that the whole core communication layer has been switched out to use an industry standard platform, and as Marcus said, where we can choose a lot of long existing implementations. But yeah, that's definitely one of the biggest thing. There's also a lot of other things that they have cleaned up in the meantime that we'll get to as well. For instance, in ROS1, you got the difference between nodes and nodelets that you would have to maintain separately. In ROS2, they combined that into a single concept. There's a lot more tweaking that you can do around the communication, about how real time you want to have things, the quality of service, which we'll also talk about. But yeah, basically they took this whole switch to the new version as an opportunity to clean up a lot of stuff that has just been bolted on over time onto ROS1, and actually do it properly and have everything well integrated with each other.
Okay. Thanks.
Great. No worries.
Great.
Great.
Just one comment here. We have a in the paper I just announced, we had a comparison between ROS1 and ROS2, which we deliberately left out here because it's quite something. But yeah, so can refer you to that also if you like.
Exactly. Yeah. Okay. I'm sure if I can. I was going to ask with a raise of hands or a yes in Zoom to see who is actually able to get the demo running, but I'm not sure if I can see that. But I hope that everybody, or at least a lot of you, have been able to go through the instructions of how to set up the environment. We already had some questions. Again, if there's any more, feel free to raise your hand up, and then Marcus will have a look at that and contact you, or go to Field C on Discord. So I will do a little bit of a demo of what things should look like. So if I start out in the WS home directory that the instructions instructed you to create, in there I have the ROS2 workshop repository cloned, and I have the .ade home file in here. I've got a lot of other stuff in there as well because I've already been running things in here. You will not have those, but those will all be created once you go through the exercises. So when I'm in here, I can go into the repository, and I will the command to force start and update the environment. If you haven't done this for a while, then it might pull in a new version of the Docker image. If you've done that before, then it should be as fast as you see here. And you will see at the end that the ADE environment has been started. So now a Docker container is running on the background, and we can get into that by running ADE enter. So before I go a little bit further, so you might see a little bit different. You might only see this one entry here, which says that it's loading the base volume of the ADE environment. I also have the VS Code one enabled because we installed a couple of editors in the environment to help you. So there's Vim, or for those who like that. We also installed Sublime editor, and you can use that to edit. I will use VS Code, so I'll quickly show how to set it up. If you are in the workshop directory, in the repository, then there's an ADE-RC file. If you open that, and then you will find an entry for VS Code by default that's commented out. If you uncomment that, then it will also load the VS Code volume for you, and then you have access to use that as well if you want to. Then you run the start command again to restart it, and then you will have access to VS Code if you so want to, but again, there's also Sublime and Vim. So when you're in here, then we can launch the simulator following the instructions, again, from the README from the repository. So we run ROS2 launch bolt sim. So this is a ROS2 package, and we tell it which launch file to use from that package. So there's a bolt sim, bring up the launch.py. Won't go into too much detail there. You can find that and look into it and see what it actually does. But when you run it, and if you do this for the first time, it might be very slow. It might be taking a long time for something to start up. That is okay. I mean, it's not exactly okay, but it's expected. And then it might be that once it finally started up, you only see a football pitch, but no robot. If that's the case, just Control-C, kill the whole thing, bring it up again, and then second time and any time after that, it should be fast, and you should almost immediately see this. So if that is successful, then you'll see something like this. If you don't have NVIDIA drivers, then everything might look a bit darker for you. The lighting of the 3D scene is a bit different there. If you do have NVIDIA drivers like I do, you get the shadows and a bit better lighting. For the purposes here, it doesn't really matter. If you want to do some sort of computer vision in Gazebo, then of course, then things are a bit different, and you want to pay attention to that. But if everything is successful, you will see the robot standing there. You will see the ball, you see the goal, and then what actually has happened is that the launch file has launched Gazebo, spawned the robot in there, has started a plugin that is loaded with the robot, and the plugin provides the interface with the rest of ROS2. So I will create a new terminal. I use Tmux. If you don't know that and you want to use ROS or ROS2, definitely learn that. It will make your life so much easier. If you don't have it, you can just create a new terminal. Make sure that you're in the right directory whenever you run commands. In this terminal, I will enter ADE again. So you will have to do that for each terminal that you create and you want to work into. And then I can inspect stuff. So ROS2 comes with a very handy command line interface tool, which is called ROS2. I mean, we already saw that for launching the simulator, but it has a lot of other features. If I just run it like this, it will provide a whole list of commands that you can do and a lot of stuff that we won't get into. But the most important one is topic. So in ROS2, all your intelligence or your logic is split up into standalone nodes, and they form discrete pieces of intelligence, of logic, and they communicate with each other through so-called topics. So one node can send a topic, can send a message on a topic to another node. Now, to get a little bit of a better graphical overview of that, there's a tool, RQT graph. When you open that, it will show you all the nodes and all the topics. So by default, and because I've run this before, it's a little bit different. By default, it will say nodes only. If you're starting this, make sure to select nodes and topics all, so you can see all of them. And also by default, dead things and leave topics are hidden. Untick them so they can see everything. If you hide them, then topics that are not being used, they're hidden, which can be useful, but we want to see everything. So one thing we see here, let me refresh because I'm not sure I got everything here. Yeah. So if you see a very limited amount of nodes, hit the refresh button and then it will update when everything is running. So you see that already now there's quite a bit of stuff that is there. So you see Gazebo, which is represented as a node. So all the elliptical nodes in here, they are ROS2 nodes. So they can be seen as independent processes that are running. And they are connected by topics, which are the rectangular boxes. And topics have names. So for instance, the Gazebo Bullbot plugin sends the state of joints onto a topic that is called /joint_states. And that topic is being read, for instance, by a node called the robot state publisher, which integrates those nodes with the robot model and then outputs a bit more about the description of the robot. So here you can follow exactly all the different topics. So we have a camera, a simulated camera in there as well, that provides a camera controller node that provides an image topic where it publishes images. And we'll have a look at that a little bit later as well. There's a simulated IMU in there, and that sends data out there as well. So this gives you a good overview of everything that's running and all the things that are communicating with each other. So the next step is, once we have that overview, we can see what is actually being sent. So like I said, in the command line tool, you have the topic command. If you run that, press enter, and it will give you more information on what you can do. And some of the interesting ones are, to start off with, is echo. Or actually, let's start with lists. So if we run ROS2 topic lists, then again, we see all the topics where messages might be sent over. And if we add -t, then we also can see the type of message. So messages are strongly typed binary messages. The schema, or the structure, are defined in special message files. We won't go into that too much, but the important thing to know is that each topic has a specific message type that's being sent over that topic with different features in there. So we can inspect what those actually are. So the message files, or they specify the interface of a topic, and we can, for instance, show. Let's take the joint commands topic. So this is a topic that uses MX joint controllers. MX, that's from Dynamixel, because that's what we're using for our robot. And we have the joint command message in there. So if we show the interface, then we get a nice documentation of what's in there and the fields that there are, and description what they should be. Let me just quickly have a quick look. Good, yeah. So now we know that these messages have this format. So join commands, they have names for joins, positions, and some PID gains that you can set. So this is how you can inspect what the messages would look like. Now, the most interesting thing is, of course, to actually make the robot do stuff. So if we go to Gazebo, if you're not familiar with it, if you click and drag, you can drag the environment. By scrolling, you can zoom in or out. If you hold the middle mouse button and you drag, then you can rotate the view, and by that you can make sure to focus on the robot. So let's see, for instance, an example of controlling the joint of the robot. If we have ROS2 topic, so all the ROS2 command line interface commands, they have tab completion, so you can run tab, and then you can get an overview of what you can run next. So we want to publish a message, so we say pub, we tab again, then we get a list of all the topics that we can publish on, and a whole bunch of parameters as well. We will use once to only publish a message once instead of repeatedly, which it will do by default. We want to publish a joint command, so we publish on the CM730 joint commands. So this is again because we as a team, we use the CM730 board, so this is a custom thing for this code coming from us. For other robots, other platforms, you might see a different topic. And then if we tab again, you can see the next thing to specify is the message type. So it already knows that we have to send joint commands. And if we double tab again, then we see the structure of the message. So this is a bit terrible to read because it outputs it as multi-line YAML, but you can also write it as just inline YAML as well. So to control the joint, what we want to do is we have to name all the joints that we want to activate, which we want to control. So at the moment, let's say we want to control the head pan, so whether the robot is looking left or right. And then together with that, we have to at least supply a list of target angles that match the list of joints that we have set. So for instance, I can say to set the head pan to 0, 0. I run that and it's done. You didn't see anything happening because it's already looking at 0, 0. But now I can change, for instance, to 1. And then we'll see the robot has moved his head to look to the left. So the position is an angle in radians. So this is 1 radian to the left. If we say -1, then we go back and it's looking to the right. And then we can return it to 0. There we go. So that's a quick introduction on how to control stuff. I don't know if there's been any questions in the meantime. I saw some things on Discord. I'm not sure if I can actually see. Can I see the hands up when I'm sharing screen?
So there was no question so far, I think. I mean, I was checking the hands up now. But...
Great. Anybody have a question that they want to put into the group at this point? Everybody following along? Anybody been able to reproduce this? So the steps to do this, they can also be found, and I probably should have shown this in the beginning, but if you're in the repository, then we have 3 folders in there for exercise 0, 1, and 2. And all the stuff I just did is actually under exercise 0. So you can actually follow the steps there if you missed out and I went too fast. So there's a question. It seems the PID parameters are optionals, right? Yes. So this is again a implementation detail of our setup, but they are optional. Yeah. So by default, just take the standard PID values that are used in the Dynamixel MX motors. And if you set those on the real robot, then you can override those by sending these messages. So you can also do it in the simulator, but I won't do that now because it'll probably mess up everything. But if you do want to do that, then you do have to provide all of them. I think that's how we have set it up. So if you want to set a P gain, you have to provide a list, again, corresponding to the joints that you've set. And then you also have to supply the I gain and the D gain. So I won't try that now. Again, not to mess things too much up, but you can give it a try if you want. If you mess it up, just restart the simulation and then everything is reset to normal. Good. Any further questions at the moment? No. Is there anybody who needs a little bit more time to try to set it up? Anybody still struggling before we go further with the rest of the exercises, where you'll actually write a bit of code and do a bit more interesting stuff yourself? Good. Then with that, then I think we can continue with the first exercise. So again, the instructions are all on the repository. You can also find it locally if you have it cloned. There's a readme.md, but it's probably nicer to read it on GitLab because you get a little bit nicer formatting. I will go firstly through the initial steps to get everybody started. We'll show the solution to the first step live. Then the idea is that you all go off, try out the exercises. After some time, I will probably just show the solution to them. Hopefully they are manageable, it's mostly a lot of text and some small changes to make. But yeah, if any questions come up, then again, anytime feel free to ask. So I start here with exercise 1. So I have keep the simulation running. So make sure that, actually I don't have the simulation running. So there we go. So we have the robot on the field again. If you want, you can remove this, slide at this. We don't really need that. Then with that running, I have a second terminal inside ADE. So I want to make sure that we're at the home directory to start off with. And then we want to create a source directory. And the way ROS works, or actually we're using Colcon to do all the building for us. Colcon is a Python tool that kind of wraps around CMake and a lot of the build functionality and macros and tools that comes with ROS2, that then actually resolves all the dependencies between packages, can make sure that everything is built in the right order, etc., etc. Definitely, if you want to go further, look it up. It can do a lot, but at the moment, all you need to know is the instructions that are here. So we have the source directory. Then in the repository, you will see, I think I might be, hold on, I think I actually might not be on the right. There we go. I didn't do the thing that we told everybody to do at the start, but now I am on the latest version. So I see all the exercise code. So copy over a directory that contains a bit of a skeleton of a package, and I'll put it into the source folder. So if we do that, then we see that there's the ROS2 sense act directory in the source folder, and it has a bunch of files. So it has a package.xml, setup.py, setup.cfg. We won't go into that too much again, but I will just quickly show what's in there. So again, here in VS Code, you can use Sublime or Vim. Let me just quickly show that as well. You can use Sublime Editor. You should. It's opened in the background. So you can use that as well and just add it in there. If you really want to use something else, you can also just do a sudo apt upgrade, and then you can install any package that comes with Ubuntu. Just remind that all that will be gone whenever you restart ADE. But yeah, go ahead and do whatever you like in there. So I will use VS Code. So a ROS package is basically a bunch of source files and a bunch of extra files that define features and dependencies and other details about packages, so that the whole system knows how everything fits together. So if you look at the one that so open package.xml, just go full screen of the ROS2 sense act package that we just copied over to the source folder, and you see some information in there like a package name, package version, a description, maintainer, license, and then some dependencies. So at the moment we don't depend on much. There's a bunch of test dependencies for if you want to run unit tests. Then those are used. These are just automatically filled in whenever you create a package, so I won't go into that. Also setup.py, if you're familiar with Python packages, that you kind of know what's in there. That's also can be auto-generated by ROS2, and it will make sure that commands get mapped to proper packages and modules, etc. So again, something for you to look into later, but I won't go into that too much, because what's more interesting is the actual source code. So in the package, there's a ROS2 senseAct Python package, and there is a senseAct file in there. Let's get rid of all these things. And this is where you will be working in. So you'll see there's already a bunch of stuff set up. There's a bunch of comments that will tell you what to do, and a lot of stuff that's commented out, and you will get all of this running. So I will walk through the first step to kind of show what that looks like. So to go back to the first steps, once we have the package copied, then I will run this build command. And basically all it does for the Python package that we're working on now is that it will create an install directory, and inside there's a package, and it installs all the stuff in there, and that's actually where it will pick up your nodes whenever you run the node with the run command, which we'll see in a second. Now, after building, and usually you have to do this almost all the time after you run a colcon build command, you have to source the setup file that gets installed in the install directory. So this is a file that colcon generates, and it sets up all sorts of environment variables and everything else that ROS needs to actually find your nodes. So once you've done that, then I'll already skip a little bit ahead, and I will actually run the node that we created. So there's this ROS2 run command. You give a package name, and that's the same name that we saw in the package XML file. There's my mouse there. So we have this package name here, and then there's a node name, which is the node name that is defined in the node file. So if I run that, at the moment it doesn't do anything, but the fact that it doesn't return says that now the node is running and will actually make it do stuff. So back to the README. So there's this interface command again, where we can actually we're here. So I've done this, environment is completely set up, and I open this file in an editor. So we're now here. So the first thing we'll do is to actually have the node subscribe to a topic. So if you remember, there are already a lot of topics that are available. And the one we are interested in at the moment is the joint states topic. I can use the command line to just echo all the stuff that is posted over there. You see a lot of stuff fly by. It has stuff very similar to the joint command message. So it has a list of joint names they can use, and a list with the current positions of all the joints, which are very close to 0 now, because that's what the robot starts out with. So now we want our node to actually subscribe to that, and that's what the first step is about. So that happens in the method that we prepared here in a subscription, and you can create a subscription by calling the create subscription method on the node that you're working in. So self.create subscription. You have to pass in 4 things. The first argument is the message type that is expected to be sent over that topic. The second is the topic name. The third is a callback function that will be called on every message, and which you can use to handle the message. And last is a so-called quality of service profile, which we won't go into too much depth in the second exercise. We'll talk a bit more about that. At the moment, we're just using the system default, which is good enough for us. So first, then we have to decide on the message type. So when we inspect the joint state topics, then we see that the type is sensor messages message joint state. In Python, you can get a class representing this message, by very much following that path. So there's a sensor messages package, message module in there, and then there's a joint state class in there, which represents the message type. So we can use that, and we just use that name directly in the create subscription command to specify the type of the message that we want to receive. So that's good. Then the topic name, we already know that. So that's the joint states. You can, I think it also works without the /, but it's a nice convention to use that. Then it's also very visible. They're talking about the ROS topic or something similar. And then the callback, at the moment, we just have a Python lambda function that does nothing. So let's make it do something. So we just make it print out the message. So once we've done that, then we can directly run the node, so we don't have to build or anything again, because we install everything with symbolic links, so everything is just automatically picked up whenever you're editing. So when we run this, then ideally we should see, what did I do wrong here? Of course, that always, silly mistake. So now we changed the things in this method. Now we actually have to make sure that this method is called. So uncomment the init call, and then when we run it, there we go. So now we see this is our node that is running. We can actually create another ADE terminal and use a tool that we saw before, RQT graph. Just refresh just to make sure everything is there. There we go. And then now we see that there's our sense act node, and indeed is registered as subscribed to the joint states topic here. And you also see that it's probably just do this T__ROS out. So this is some built-in topic for logging stuff, but we're not using it at the moment. You can see all the information being printed here. And if we look a bit further up, then we see exactly what we expect. So we see a joint state message with all the names, all the positions, etc. So these are the steps that are needed to set up the initial subscription and to do something very simple with the initial message and how to run everything. So with that, I'll let you all go to step 2, where you'll actually write a little bit of code to publish to the topic. So I will leave that at here. If there's any questions, you can hear the dinging that there's already stuff coming through. We'll now both be there to answer any questions. In a little bit of time, I will go through the step 2 and show the solution before we go on to step 3 and step 4, step 5. So good luck.
How does ROS2 handle the whole we only need one master and one ROS master issue? So basically in ROS1 it was always, yeah, you start your ROS master in some separate terminal, or you start with the ROS launch.
That doesn't exist. So there's loosely coupled. So the nodes are can be actually executables by itself. So there's no master this time. So that's actually one of the core benefits also. So you can just put up what you want and close when you want. There's no central.
Yeah. So, but also with that, so by default, the behavior is probably not what you want in a RoboCup team, but where all the nodes can auto discover themselves on the same network. So you can just run nodes on different machines on the same network, and they will just work and communicate with each other. Of course, if you have them running on multiple robots, then you don't want to have them interfering with each other. So there's some functionality, and there's actually also at the DDS layer where you can specify separate domains. I have to double check if they made much advancement in that in Foxy, but you can set an environment variable on each robot to give an index of which domain it is in, and then only nodes that are in the same domain, those can communicate with each other. So for instance, if you're on the Wi-Fi with 5 different robots, you set them up to be in different domains. Then on your laptop, you can set domain 1 locally, and then you're directly connected to everything running on robot 1 if you want, and then switch to the other domain. There's some other, so DDS supplies a lot of other ways to then also allow communication between robots in different domains. So for instance, if you have team communication, you can then also use ROS topics for that. Because I'm not sure if we talked about by default, all communication goes through UDP. So you could use that in a competition setting as well, and have team communication just as normal ROS2 communication. But in previous versions, they hadn't set it up yet. It was either all the nodes can talk to everybody, or only the nodes in a domain can talk to nodes in the same domain. But I know that they've been working on that to expose that DDS functionality in ROS itself. Okay, so let's go through step 2, and so I'll show who hasn't been able to go through yet what the idea is. So now we don't just want to subscribe to a topic, we want to publish to one as well. This is set up in the init publisher method, and to create a publisher is very similar to creating subscription. So you call the create publisher method on the node itself, and you supply very similar things. So again, you have to pass a message type. Now we're not interested in the joint state, but now we actually want to send joint commands. So look at the types, and we already imported that here. So we've seen that before when I ran the ROS2 command line interface to publish a message. Then that message was type mx joint controller messages message joint command. So again, we have that available in Python as well. So we can use that type in here, and then we have to specify the topic. So the commands are what we've seen, probably some topic that we've seen before. So that's the CM730 joint commands topic. And then we have the publisher set up. So next we actually want to send a message. We can just create a message like this, as thoughtfully. And then we have to actually provide some information in a message, because if you just create a message, it's just completely empty. The joint names and joint positions are empty. You can still publish it, but it has no effect. So we have to fill it with some data. So the message has the names parameter, like we saw before as well, and we have to pass in the names of the joints that we want to control. So at the moment we're controlling just the head pan, and we have to take the position and give a list of the same size and give it a value, and then the message is published. Now we make sure again that this method is actually called. So then if we go to the simulator, and I zoom in a little bit and run the node again, joint command has no attribute names. That is correct. It is actually just name. That's a convention used in more places in ROS, that even though it's a list, it uses the singular. And there we go. And we see that the robot has indeed looked 1 radian to the left again. If I change the code to -1, and we run it again, see the robot run to the right, or look to the right. And in the end, I will set it back to 0 to make sure that the robot starts out looking straight ahead. So there we go. So that was step 2. Hope that was easy enough. Then next step is to actually combine these things a bit better and to take the messages that we subscribe to, read some information from there, and decide what we send on the joint commands topic based on that. So that will be step 3. Okay, so we got a few people who seem to have managed with step 3. So I will go through that now. If there's anybody who thinks, no, stop, going too fast, don't spoil it for me, then let me know. But let's have a look at step 3 right now. So the idea there is that we don't just print the messages, we actually do something useful with them when they come in, and we actually handle them. So the first thing to do is to see we created a handle message method already for you that does a lot of the handling possibly. So we want to use that instead of just printing out the message when it comes in. So where we do that is we go back to the create subscription call, where we create the original subscription, where before we just output the message, but instead we use the handle message function here. So we can pass it in like this. So the function is on the node, and we just give the name of the function. So make sure you don't try to call it or something. Just give the name, and then that is used as the callback function whenever a joint state message comes in. So when we then go to that function, the message is supplied to the function, and we want to get some information out of that. So we know there's all the joint names and positions in there of all the joints of the robot. So we can access the position list and index that with whatever joint we want. So ideally, in your own code, you look in the name list and check the names and make sure that you're using the right index. We know that the angle that we're interested in, the head pan, is at index 6. So we grab that here directly and put it into its local variable. Now what we want to do is to create a new message just like before. And we say which joints do we want to control. So this time we want to control the head tilt. So that's the joint that makes the head look up or down. And what we want to do, not sure if it's the most useful thing to do, but we just want it to track the current head pan. So again, so we get the current pan from the sensors, and then we just set a head tilt to track that, and we publish the message. So if we do that and we save and then we run again, this is not correct. Yeah, of course, should be equals to actually assign it. There we go. So we don't have any output now because we removed the print callback. But now when we let's find the command, when we publish a new command again, just like before, so we publish a joint command with this type, and again the head pan, and we say position 1. Then now we see that not only does the robot look to the left, which is we told it to do based on head pan, but actually the feedback loop reads the head pan, and based on that, it also sets the head tilt. And you see that a head tilt of 1 means that the robot is looking down. If we do the other way around, there we see that it goes from bottom left to top right, pretty jerky. But you can see that there we got a full loop together now, that it acts based on the sensors and controls at least one of the joints like that. So that is step 3. Then in step 4, we will go a step away from controlling the head pan by hand, by sending it single messages, and actually making nice, smooth movement by using a timer.
About the timer, the smooth movement happens by basically reading out the timer and keeping basically the angle linked to the time. Is that how it works?
Pretty much, yeah. So if you look into the function, where you go a little bit ahead there, but you'll see it gets the current time, and then it determines a phase based on that time, and just uses a simple sine function to turn that into a position multiplied by some amplitude. So you get a nice smooth oscillating function, and that indeed is fixed for the time. So it develops smoothly over time. One thing to note here is that in ROS, I think at the moment it's fine, but you have the difference between real time and simulation time, or actually it can be any virtual clock that publishes the time. So you see here that Gazebo has its own time. I've now been running this for 51 minutes of simulation time. The real time factor is 1, so at the moment that's actually real time. But if this is smaller, then this time will go slower than real time. But then the time that you get here from the clock will then automatically be the time from the simulation. So you don't have to worry about simulation not being in sync with real time. You still have ideally the right thing happen.
And in real life, the time would come from where?
From the system clock. So then it will the time will be in I think it's seconds from epoch by default.
Excellent.
Okay, it looks like a bunch of you have already been finished with step 4 as well. So let's quickly go through that. So as you mentioned, instead of responding to messages coming in, you can also have the system respond to time. So you can set up a timer that triggers an action at every fixed interval, and then do something interesting. So most of that already implemented. We'll enable that by uncommenting these lines. So we set a variable, an attribute with a period, which we measure in seconds. So we by default use 4. We set an amplitude. This will be the amplitude of the oscillation that the head will do. We set that to 1, and then we create the actual timer. And again, it's very similar to, for instance, creating a subscription, but rather than specifying a topic and a message type, you specify a period of time that triggers the callback function that you supply. So here we say the period is 0.02. It's also measured in seconds. So this will create a timer that fires at 50 Hertz. And every time it will call handle tick. So in there, we've already seen a little bit when Daniel asked the question. So we get a time. Each node has a get clock method to get a clock that can tell the time. You can ask for now. That gives you a structure that has the nanoseconds member that gives you the total nanoseconds, and you can divide that by 10 to the power of 9 to get a number of seconds. We do some calculations to turn that into an oscillating pattern, get a position that goes from minus amplitude to plus amplitude, and then we do exactly the same as before. We create a joint command message We want to control the head pen to look from left to the right, set a target position, and then we publish the message. So hopefully all that should just work. Let me actually save. Put the robot up again. Being a little bit wonky. So we'll start that. And there we go. There we see. That will go from -1 to 1. And again, realize that we're only directly controlling the head pen in this sense, but the head tilt control that takes the sensed position from the motor, from the head pen motor, and then set the head tilt angle that is still running. So there we see is also looking up and down in the same oscillation. So you see that the robot is a little bit wobbly. Our real robots will probably not be as wobbly. There's still a bunch of parameters they can tweak in Gazebo to make it more stable. Probably made the head a bit too heavy on this simulation, but that's still a work in progress. Anybody who's continuing with this and tweaking this, also very happy to hear and get some merge requests with any fixes that anybody might find. But this is step 4. And then step 5, the last step, is to introduce parameters. So parameters are a functionality in ROS and also ROS2, in which you can set different properties of your behavior, either override some defaults when you start the robot, or actually change them while the robot is running. Stuff that all of us have done in competitions, I'm sure, to tweak settings of your walking algorithm or your get-up scripts or anything else like that. So yeah, let's go on and let everybody a little bit of time to finish up that final step. Okay, I think maybe people are finished up with step 5 as well. If not, then again, do stop me. But then let's quickly go through that and finish up the last step of this exercise. So again, the idea is to create parameters with which you can control the behavior and some of its attributes. So a lot of that is provided as well. The functionality that ROS2 gives you are these parameters that you can declare. So to declare one, you just do self.declare parameter and you give it a name. So here we give it a name period, and then we give it a default value. Probably something that makes sense is to actually use the local variable, or actually the member variable that we use to store the period in as default value. But just to make clear what's going on, I kept that here. Now, once you've done this, once you've declared a parameter, then at the moment it just takes the current value and you can request that, and then you can only set it whenever you start a node, which we won't show because it's not so interesting. But actually you can also register another callback function to respond to requests of changes of the values of these parameters. So the way you do that is you call the add on set parameters callback, and then you pass in a single callback function. So for any parameter change for any of the parameters, the same function is called. So it's not one per parameter, but can be multiple at the same time. So a single function is being called. We have specified that as well. So there's the handle parameter function, and it gets a list of all parameters that are requested to be changed at the same time. So usually there's just one, because you only call to change one at the same time, but it could be multiple ones. So that's why you get a list, and then you can iterate through the list, and then you can check each element in the list if it fits the name that you expect. So here we again are interested in the period. Then if we found the right parameter, then we get the value that has been requested, then we can store that in our attribute, so that then later on here again, if you remember, in the handle tick function, this variable is being used to determine the phase and the final position of the headpan node. The last thing to do in the callback function is to return a set parameters result object to say whether everything was good or not. So for instance, you can do some value validation if somebody tries to give a period that is way too short or any dangerous values. You can say successful equals false, and then the caller will be notified that setting the parameter failed. But for now, we'll have that. So if we bring back the robots and we restart the node, so it keeps on running again. Now we can use the ROS2 command line interface again. So we've seen the topic verb. Now we use the param verb, and there you can see all the things you can do. You can list all the parameters that are available across all the nodes that you have. Let me make this a little bit bigger. So you actually see that by default there are already quite a lot of them. Gazebo has some, different plugins have some. All of them have this use sim time parameter, which is set to true. So we actually use a sim time, simulation time, as I mentioned before. But we also now see the parameter here in our sense_ect node for period that we can interact with. So we can get the value of that. So we say which node it is, and then which parameter we're interested in. And then we'll go and ask the node, and we'll say the current value is 4. So we have a period of 4 seconds. Then we can also change that and set it, and we set it to 2, for instance. And then we can see that the head now moves twice as fast, and the oscillating motion has a period of 2 seconds. You can also slow it down, a period of 8 seconds. And there we go. So this is a way to update any parameters for any of the behavior that you have. You can control it on the command line interface. You can also have nodes make these calls to each other. So one node can set the parameters on another node if you want to. There's a lot of possibilities. Yes, Jasper.
So in ROS1, we had dynamic reconfigure. Does that basically replace dynamic reconfigure?
Yeah. So things work a little bit different. So in ROS1, you had a parameter server. I think it's the name, if I recall correctly. So a separate entity where all the parameters are maintained. Here now everything's integrated into the nodes themselves. And indeed, this then kind of replaced that you can dynamically reconfigure any parameter that is available. It doesn't work for all of them. So to have that work, the node actually has to do this registration of a callback function. If you look into many nodes that are out there from standard packages, not all of them do that. So then you can only change the parameter value at startup, which is, if you're familiar with ROS2, also kind of similar. But you can do that a command line. So whenever you start a node, you can supply extra ROS args. One of them is param, and then you can say period, and you set it to, let's set it to 2, and then that should have the same effect, which it doesn't by the looks of it. So I'm probably, off from the top of my head, using the wrong construct. Yeah, so I think because that's the case, because in the code, when I register the parameter here, or declare the parameter, then I get a parameter object, but I don't actually check the value of that parameter at runtime. So let me just quickly check if that's the case. So actually I can try to get that period we're looking at. Let's see if that does it. Yeah, there you go. So that's faster. So then So there you can set it during runtime, and then now I can also override it and dynamically reconfigure it to a different setting. Good. So I hope everybody was able to follow along. Some of you went through quite fast, so that was very good to see. If you look at the README, there's a bit of conclusion about what we've done, and maybe also some other things that you can try if you're interested in. So you can create another parameter to not only control the period, but also the amplitude. You can make some different motion patterns. Maybe you can try controlling more joints at the same time. And then there's also some other things to read up on. So at the moment, we're only using topics that are a little bit send and forget. So you send a message and you have no idea, you don't get any feedback, whether it's successful or not, or if the robot actually does what you want it to do. So on top of topics, ROS2 also implements other communication methods. So one is services, which basically means that there are two topics, a topic to send commands to a service and a reply topic where you can see if any replies come back. And then there's a lot of logic on top of that that hides this kind of topics underneath. So you can use services. I can use one, for instance, if you look at the command line interface again, there's a command for that as well. You can list all the services. And if it's a gazebo, has a couple of services. It has, further up, there's pause physics and unpause physics. So I can, for instance, call pause physics, and you have to give it a message as well. So at the moment, so this just requires an empty message. And you can see by calling that, I've paused gazebo. And the nice thing of services, and this is not a good example, but it's the only one that kind of is there at the moment. A service also gives you a response. Usually gives you something useful, but at the moment it just gives you an empty response, which here then implies that pause in gazebo was successful. But it can be anything. It can be some feedback information, whatever that could be useful. For instance, you can use this if you have a sensor that you don't call continuously, but you want to trigger a reading of the sensor once. Then you can make a node that provides a service. You call that service, the node guesses the sensor value and then sends a reply back with the sensor value. So that's one thing. I can now unpause this as well. And then there's also actions, and they are even a bit further. They're kind of like services. They can give you some feedback, but actually they can give you update on the progress of some action. So for instance, if you have an action that is taking a full walking step, then the calling node can get an update on how far advanced that step is and other status updates, and then you can decide to cancel that action as well. So interesting things to read up on. Other things, launch files. At the moment we're running nodes by hand, all of them separately in a separate terminal. Of course, you don't want to do that for your robot. You want to combine everything in a single command, and that's where launch files come in. In ROS2, these come in different flavors. So you can have simple text files, so they can be defined in YAML. It's quite succinct, but actually you can also create complete Python files with all sorts of logic that decide which nodes have to run how based on whatever kind of conditionals or situation you're currently in. So definitely that's worth looking into as well. With that, we get to the end of the first exercise. Again, people want to continue play with the actual robots or the simulator robots, please feel free, go ahead. Maybe we'll give 5 minutes and then we'll go into exercise 2. And exercise 2 is advanced ROS2 feature. So this will definitely be a bit more advanced. We'll be looking at C++ code. We'll fiddling a little bit with CMake files and a little bit more advanced concepts. So anybody who wants to drop off, feel free to do so. Or like I said, continue with playing around with the simulator robots. Let's see if somebody can make it do something interesting. It would be great to see somebody at the end of the workshop implemented some nice behavior. But yeah, we'll take a quick 5-minute break, and then I'll introduce exercise 2, get everybody started, and we'll go from there. Okay, and we're back again. I hope everybody is still with us too, and ready for the second exercise. So the first thing to do here is to kill the simulator. We were hoping to do this exercise using Gazebo as well, but because we'll be looking at fine-grained timing and monitoring of topics, that didn't really work very well with the simulation time. So we'll be using a little bit of a different setup, and we'll have a look at publishing and processing images, and using that to talk through the topics that we'll have a look at here. So again, the instructions are on GitLab. So on our repository, under exercise 2, there's a README again, and we'll follow along with that. So we will discuss 2 main topics. There's a lot more around ROS2, but there's only so much that we could fit into the limited amount of hours that we have, and the limited amount of attention span that everybody will probably have as well. So the topics that we'll be talking about are quality of service and node composition. So to start off with quality of service, we already saw it in our code a little bit in the previous exercise as the parameter that you have to pass in when you create a subscription or when you create a publisher. So as we mentioned before, the underlying communication in ROS2 is based on UDP. So this can be classified as best effort communication. The messages can be sent, they don't necessarily have to arrive in order, and messages can be dropped if you're communicating over a lossy network. But the DDS system on top of that applies all sorts of methods and a lot of settings with which you can still guarantee a reliable communication and basically get something much closer to what you would get with TCP, for instance. And you can get a lot of different great levels of reliability and real-timeness in between. So we'll look at some of those features and how to tweak those to make sure that the communication between your nodes are of the right type and have the correct limitations or requirements, etc. Node composition. So this is something that might be familiar for ROS1 people as well. So at the moment we have run nodes, or actually just one node, but we've run them as completely separate processes. So as you remember, we call the ROS2 run command to run a node that starts up a whole new process. And all those nodes are running completely separate and then using the whole communication layer to communicate with each other. Of course, when you're running on a robot, that doesn't necessarily make sense. You don't want to have 200 processes possibly. Maybe just want to have a single process. So ROS2 allows you to compose nodes into a single process, very similar to ROS1 nodelets. But in ROS2, so this is one of those things where they rethought everything and did it correct from the start. In ROS2, you don't have to make that distinction when you're developing your node. You just create a node, and then at runtime, you can decide whether you want to run it as a separate process, want to compose it into a single process, and whether you want to have that composition done dynamically at runtime or maybe more statically defined in your code. So we'll have a look at that, and that will have some benefits, like it will be able to have very optimized communication and also some other useful features. So let's get into that. I will go through the first step. Then again, we'll let people see how far they get and questions that come up. So because this is a bit more advanced, maybe things don't work as well. Definitely, if something doesn't work, let us know. But let's get started with that. So we start out, and I will refresh, I'll close some of this. We'll probably open them, but let's clear just to start fresh. So again, we start in the AD environment. Just make sure we're in the home directory. We have the example code to get started with in the directory. So we can run this, but we already created a source directory for the previous exercise. And let's copy the base code that we've prepared into the source directory of your workspace. So now in the source, we've got our previous package, and now we've got our new package. And if we look at that, then we see very familiar. There's a package.xml, but now there's a CMake lists, a CMake list.txt, no setup.py, etc. Because now we're working with C++ rather than with the Python interface. So again, we use callcon to build and install this package. The command is a bit longer. You can, in theory, just run callcon build, and then it just builds everything. But just to make sure everything is configured correctly, that we use release settings, so everything is optimized, and then we only build up to the package that we're interested in. We run this whole command. So if we do that, you see it's actually compiling the package. The first time might take a bit longer. It's incremental, so later on it might be a bit faster. But now we're finished, and the package is compiled as before. And again, make sure you do this in every new terminal in ADE that you open. You have to source the local setup so that the package becomes available for the ROS command line interface, etc. Now that we've done this, if you've done this, we'll have to run the callcon build command a few more times to recompile C++, because that's something I don't have to do for Python, but for C++ you have to do that after every edit. You won't have to run the source command after every time. In the documentation, it will say when you have to do that. If you still want to do that, just to make sure it doesn't hurt, so you can throw this in any time that you want. Now that we have this running, we have this compiled, we will start running some nodes. So the first one is, let's see, we got a command from Jan. Package was not found during callcon command, but it's there looking with ls. And maybe Marcus, if you can help out, I'll just quickly go through these steps. So we'll be running a few nodes. The first is a node that comes with ODE, or actually a separate ODE package, but that you can install with apt-get, which is the image publisher node. And we will publish an image. There's a workshop banner.png, which is the image you will see in the main README. But you can pick any image if you want to throw another image into your environment. By all means, to do that. But this one is a nice one because it's a bit big, so we can more easily see any latency issues or things like that. So when we run this, you should get some output as following. So everything should look fine. It will pick up the file name, and it will say it will not flipping it either horizontally or vertically. To see this in action, so we haven't looked at that too much yet, but we can use RVisp, which if you went through the initial setup, you've seen that with the dummy robot. But this is a very comprehensive visualization tool that comes with ROS. So if I start it, first there's nothing, but I can add a display based on a topic. So we see here all the topics that get published. We are interested in the image raw topic that gets published by the image publisher, and then the image specifically. So there's also camera one. We won't go into that, but if you have a camera with calibration settings, etc., then you can use that, and then you get all that information. But we just use the raw image. Now, initially, you won't see any image. This is because we have to specify the frame, the coordinate frame that this comes in, which is the camera. And there you see that now the image gets shown. So it's a very boring image, and it's just a still image, but it's good enough for our purposes to go forward. So if then we have that, we start another terminal. Get a good size, there we go. And in there, we run the node that comes from our code, and that's the image reader node from the ROS2 advanced package. So we run that. And I didn't do what I told you should do. So in all new terminals, make sure your source is set up. And with that, it's actually running. And what it does, we can again go into another terminal. So here you can see where something like Tmux definitely helps. You'll end up with tons and tons of terminals. Look at the graph. Just refresh to make sure we got everything. So now we see that we have the image publisher node, which publishes on the image raw topic. And then we have our image reader node, which subscribes to the topic. And what it does is outputs another image topic called workshop image. And here you can actually see also that RViz is subscribed to the image raw topic as well, which indeed it is, and that's where it shows here. So what we can do now actually is we can add another display here. So we see now that the workshop image shows up in RViz as well. We can select the image there. And then what we have to do there, and that will become clear a little bit later, but we have to switch the reliability policy to best effort. And then we can see the image that is being shown there. So as you'll go through the code, you'll see what it does. It just does a simple inversion of the colors of the image and republishes it. So much for the first introduction. I will let everybody go through the rest of the exercise. It will not involve too much code. Most is text and some commands to run. And then hopefully you'll see some effects that we're talking about and see where quality of service profiles are useful and how you want to use them and the benefits that it will give over just very simple communication. I'll check in maybe in 15 minutes or so to walk through it. But yeah, anybody, again, hitting any issues, fire off a question and we'll try to help. Okay, so just to go quickly through the quality of service section. So looks like everybody's been able to go through that and no major issues. So let me just this and go through it quickly as well. Get everything back into place. Good. So the section kind of tried to show the effect of different settings on the quality of service. So if anybody have had a look at the official documentation, there's a lot more that can be configured than what we're talking about here. So at the moment, we've only really been looking at the reliability. It's one of the more important ones, whether we go for best effort or for reliable communication. Also the history and then the depth of the history. So basically, if the node is too slow in processing messages, then they can be buffered in a queue up to a certain size or indefinitely, where keep all is of course a little bit optimistic because you still have a limited amount of memory and it will blow up at some point if the node doesn't catch up. There's also a bunch of other interesting ones. For instance, there's durability, which controls whether messages that were sent before somebody joined the topic will be replayed. So if people again familiar with ROS1, familiar with latched topics, then this is how to implement those. So these are things, for instance, if you have a map of the environment that you don't want to publish continuously and never changes, just want to publish one, and any topic that subscribe or any node that subscribes to the topic should then only get that map once, and that's it. So what you can do is you can specify the topic as being transient local, which means that the publisher is responsible for persisting samples. And then you can set the history depth to 1, and then it will just keep this one example of the map in memory. And then whenever there's a new node or anything that subscribes to the topic, we'll then only get the single message, even if they join late. And then there's things like deadline, lifespan, liveliness, which are all there to help you review the healthiness of your node and to make sure the messages are sent in certain deadlines and ignore otherwise. So what we've done in this exercise is we measured the frequency that the raw image gets published in. I think some of the messages in the chat channel, those look like good numbers. So the image raw one should be published by about 10 Hertz, and the workshop image a little bit less because we are sleeping in that time. If I can actually reproduce that, so I will start the publisher here, and I will start the reader here as well. If I have sources. And then I can run ROS2 topic Hertz image raw. And then we see that comes in close to 10 frames per second. There's some hiccups in there. And part of that is the ROS2 command line interface. It's written in Python, and it's quite a big image, so it might not keep up. But we can definitely see the effect, the difference between that one and the output of the processed image, which here I get about 4 Hertz. And if we can also look at the delay. And we see that the image here gets a delay of close to 1 second, whereas as explained in the text basically comes because the node can't keep up with the messages. It has a queue of 10 messages. There's a new message coming in every 100 milliseconds. So at some point, it keeps on reading 10 messages behind, and it ends up with a delay of 1 second. And if we change the quality of service, then let's save that for now. If we go to the reader, and we see that we have the quality of service profiles for the subscription and the publisher here. And basically here we set a queue of 10. If we set it to 0, and we rebuild. And then we run the publisher again. We run the reader again. And now we look at the delay of the workshop image. Now we get a delay instead of 1 second, we get a delay close to 200 milliseconds. which basically means that every time it's skipping one image and is always basically two images behind, because it takes longer to process one image. But if we look at the rate, it was already pretty low. I didn't expect it to be that low on my machine. But so yeah, now the effect is not so strong, but now it's even clearly lower than the 4 frames per second that we get on this topic, because now the node ends up waiting quite a bit of time for the third image to come up. Once it processed the first one, it missed the second one, and then it's waiting for the third one to come in because it's not queuing anything. If it did have the queue, then after processing the first one, spending too long, it would still pick up the second one. So there's less waiting. So there is a higher throughput, but the latency builds up over time. So that's the trade-off that you have to make there. So that was kind of the main takeaway from that section. Then, and also I won't go to too much detail. You will have seen that, but that you have to make sure that the profiles from both the publisher and the subscriber match up, and also there you can make this decisions to either just accept everything. So if you're creating a package that you publish to other people, you create a publisher in there, you can decide to publish with a reliable level, which means that you accept up to any level. Even if you subscribe with the best effort level, then you can connection still succeeds, or you can limit to best efforts because you don't want to deal with the overhead or anything else, and you want to force every subscriber to use best efforts, then you can use that as well. So yeah, a lot of things to tweak, but it also gives you a lot of freedom to set up your system in the most efficient and in the correct way. So then the next section is about node compositions. You know, already some people been able to make progress on that. Any questions there that have come up? We got about a bit more than 10 minutes officially in the workshop. I'm also happy to stay online, definitely on Discord and such, to work on this further if people haven't got this far yet. And it's also worth for this and for anything else to open an issue on the GitLab repository. That would be very helpful for us because we also use these material internally in the team. So any issues that we find here, they'll help us, and the whole repository will stay there and stay open. So we'll help anybody else coming there in the future as well. So by all means, anything that comes up, throw it in there. All right, okay with it. I think one of the more important ones, because the dynamic loading of components that we see here, that's of course is nice. But actually it's nicer, even you can put it into launch files as well. And then you don't have to run these commands manually again, and everything will be loaded in the same process as if you created the whole system in one go, but actually you have all the separately developed nodes and they get loaded in a process. But one of the very nice things is at the end of the exercise, and yeah, at least that would be good if people get to that and get the same results. So you can also statically compose nodes where, if you look at the code, and in the normal C++ way of creating a single node, you do it like this. You create your node in a separate class, and you include that. You create a node as a shared pointer of that type, and then you just say RCL-CPP spin this node, and it will indefinitely just loop through and do its thing. Now, if you want to compose multiple nodes into a single process, then it looks like this. So you create two nodes, you can, or as many as you want, in your single main function. So we see that they are of the same type, so create two image readers, but they have some different parameters, basically trying to map the input and output topics so that one in the end reads from the other. Add both nodes to an executor, So we use a multi-threaded executor. You actually also have a single thread one, and possibly also some other ones nowadays that I haven't looked into recently, but usually you want to use multi-threaded because otherwise you can have some big interference between the two nodes. And then you spin the executor, and then that runs the event loop for both nodes. So let's give that a try. If that works, so I start a publisher again, and let me close some of these. Let's close ROS for now. Okay, make sure that's sourced, and then once we run the, let's see if I actually have it in there. So we have the compose readers nodes. So here I see exactly the same thing as before. So for some reason, only getting the output of a single reader. Let me have a look at our Qt graph. So here we do see that the image raw comes in, image reader publishes to workshop image. The second one reads from there and then outputs onto this topic. So there's some, no, it's just a single reader that does that. So maybe I'll also just try a restart, see if that works. If not, then we will wrap it up. And maybe if any further questions have come up now, then please feel free to ask now, and we can answer those. Okay, so we'll go into why that actually doesn't work. If anybody did have that working correctly, then also let me know, so I can see if it's my setup or not. But yeah, ideally you should have seen something as in the README, where you have outputs from both the readers and with the same message timestamp, and where you can see that image reader 1 publishes a message, an image message, where the image is at a certain memory address, and then image reader 2 reports that they get an image and receives it at exactly the same address. So this would then show, if it actually did work, that this allows copy-free message passing between nodes. So again, maybe something people recognize from nodelets in ROS1. But now with this so-called intra-node communication, there is no further overhead. There's no network activity or anything in between. So that will allow you to create a full software stack as if it's all just put into one system, which is pretty nice. And also in our papers, our paper from 2 years ago, where we showed some, no, that's actually from last year, yeah, where we indeed show some of these effects in terms of timing, and especially for image processing and other large messages, that's very beneficial. So we'll look into this. We'll probably file an issue for this issue, try to resolve this. So keep an eye on that if you want to get this fixed and try it out. But hopefully this has given everybody a little bit of interest in ROS2. Hopefully show a little bit how easy it is to work with it, how easy it is to bring up a system for people that are not very familiar with everything. They can start out with simple Python scripts or even just a small command line interface activity. And for people who are a bit more advanced and to really get into the nitty gritty, they have full access and a lot of things to tweak and work with to optimize and make everything work best. For anybody who wants to continue, again, we'll be on Discord, send some messages, file some issues. We have made a bunch more packages public. So let me actually sign out so I can also see exactly which ones we have public or not. So if you go to gitlab.com/boldheart, you'll find the workshop repository there. We have the BoldBots repository that provides a simulation. We have some other things like a package that wraps around Robon's IK walk system and makes that available as a ROS2 package. We've been working on some TensorFlow Lite package so you can use deep neural networks directly into your ROS2 system. IMU tools. We've got a wrapper for the 3D SimSpark simulator as well. If anybody's interested in that, a video for Linux 2 driver and a node that interfaces with the game controller as well. So a lot of this is still in development. So very happy to hear any issues, any feedback and everything on any of these. So yeah, I hope that everybody enjoyed that and learned something. And thanks so much for your attention.